Hey, this is Mr. Boyce, and I'm going to go through our review assignment. Hopefully, you've already attempted to do this on your own because you'll get a lot more out of it if you did at least try and do these problems and then see where you have an opportunity for improvement. Remember, this is a completion grade, so mistakes are just fine. So I highly recommend if you haven't done this, turn this video off, try and do this on your own, and then come back and see how you did. For now, I'm going to go ahead and move forward though and work on this with you. First off, you'll notice when I put it into Notability, we have these weird little question marks here. That's just what Notability changed the arrows to. So just think of them as arrows. That's what they all are right now. So the first problems we're dealing with decomposition and synthesis reactions. Question 1 through 4. These are all synthesis reactions, and the rest of them, 5 through 10, are decomposition reactions. So they're going to follow different rules. Now, barium and oxygen, this is just oxygen, and that's going to turn into oxide. And so this would be called barium oxide. Okay. Same rules, a -1 charge, and sodium forms a +1 charge. And whenever you put together ionics, your positive cation needs to come first. And so in this case, it would be sodium, and then bromine turns into bromide. And notice how easy it is even for me to make those mistakes. So be careful, make sure that you're putting your positive cation before your anions. Okay, in this case, sodium, which we already know is positive, that's great. It's going to put that with phosphorus, and that's going to turn into phosphide. Sodium phosphide. Let's see if we can make this pen a little smaller. Okay, and then finally, silver with iodine. Silver is our positive cation, so silver iodide. And that does it for our synthesis reactions. So now we're going to go into decomposition. And I have to warn you, the first two are decompositions of polyatomic ions. Notice I don't have an ide, I have an 8. And with the exception of hydroxide down here, that does end in an ide, but hydroxide is a polyatomic ion that you have to look up. But most polyatomic ions are not going to end in ide. So if you see an ide, or if you see anything other than an ide, you want to look up and see what it is you're dealing with. So chlorate, this is your list. Okay. And chlorate is right here. This is ClO3 with a -1 charge. Okay. And so you're going to think of that when you're putting it together as one unit. However, this is a decomposition reaction. And I have to warn you, we haven't done much on decomposition of polyatomic ions, so I do want to go over it with you, but this won't be on the Unit 5 exam, at least not the polyatomic ion part, but we will see it again later, and so we will be working on these. So this is a good time to be exposed to this. So let's take a look at what's happening here. Calcium has a +2 charge, and chlorate, as we just looked before, 3 with a -1 charge. Okay, so when this decomposes, the oxygen is actually going to split away on its own. Okay, and so what's going to happen is chlorine, if you look at your periodic table, you'll see that chlorine forms a -1 charge, and oxygen is going to split off onto its own. Okay, and so what you're going to end up with is calcium chloride plus oxygen. And if you were to put that together as a molecular formula, you would do calcium plus the chlorine, right? So we would do our little swap drop there. And that would be CaCl2. And then the oxygen is diatomic. So when it's on its own, it's always going to be an O2. So that's how this would look in a molecular format. Tin 4 chlorate. Okay, so that's going to do the same thing. Okay, it's going to split off and leave water. So we're going to end up with tin 4 chloride plus oxygen. Same thing as in the last one. Okay, so now we're into what we've seen a little more, zinc phosphide. So that's going to break apart into zinc plus phosphorus. So you drop the iod when it's on its own. Kind of a big word, but it's written on your periodic table, which is very helpful. Okay, copper 1 hydroxide. This one is also one I'm just going to go ahead and show you, but don't worry about this being on the next test. So copper 1, copper 1 would be Cu with a +1 charge. That's what the Roman numeral means. Remember, copper is one of our one of our variable charge. So here it is right here. Oh, oops, sorry, that's not copper. Oh, here's copper. And so that could have a +1 or a +2 charge. And when you write it as a formula, that becomes much more important. But here, not quite so much. And hydroxide is, oops, and in this case, what happens is the oxygen and the hydrogen break apart, and the copper will bond to the oxygen, and then the hydrogen will actually bond to other hydroxides and form water. So again, I just want to make sure that I show this to you, but I wouldn't put a question like this on the test because we didn't really cover decomposition of polyatomics in enough detail to do that. So we're going to end up with copper 1 oxide plus water. Okay, nickel 2 bromide. This gets a little bit easier now. This is just going to break into nickel and bromine. And when it's not actually connected to something, it's just considered a metal. It's on its own. Charge is no longer relevant. It's bonded to itself. Okay, and then iron 3 oxide is going to break into iron, solid iron, plus oxygen. Yeah. All right, let's start balancing. This is kind of fun for me. I like to balance. So here I don't have any polyatomics or anything that stayed together. All I have to deal with is sodium, iodine, and fluorine. Okay. So let's take a look at each one. I have 1 sodium on the left side of the arrow, and thankfully the arrows and not question mark showed up here. And I have 1 right here. So for now, my sodiums are balanced at 1, and I'm happy. For iodine, I've got 1 here, and I have 2 here. Notice this has a 2 as a subscript. Now, what I cannot do is mess with subscripts. I can't just come in here and put a 2 there because when I put together sodium and iodine, sodium forms a +1, iodine forms a -1. That goes together as a 1-to-1 ratio. So NaI2 is not a thing. I can't make that. But what I can do is go ahead and put a 2 here. And now I have 2 on both sides. Now that changes my sodium, but I always want to finish and go to the end before I start trying to go back up to something else. So let's take a look at my fluorine. F, I have 1 here on the right, and I have 2 here on the left. So I'm going to go ahead and change this to a 2 so that I have 2 on both sides. And doing that, now that I go back up and take a look at my sodium here, I had 1 on each side, but now I have 2 on each side because of my coefficients. So those are good to go. Iodine, I have 2 on my product side right there. And I have 2 on this side, because this counts for everything. Okay. And then my fluorine is also balanced. So now I am good. If the question asks for the coefficient, my answer would be 2, 1, 2, 1. Okay. All right, lithium hydroxide decomposing into lithium oxide and water. Okay. And this is why I wanted to show you the other decompositions earlier. So predicting it, we may not have covered that much, but this is what an actual decomposition looks like. All right, so let's get out of the way. Got lithium, and notice the hydroxide doesn't stay together on both sides. Now, I'm going to break them apart then. So I've got oxygen, I've got hydrogen. So those are the 3 that I have, and I have to have equal amount on both sides. So let's go ahead and start balancing. Lithium, I've got 1 right here, and I have 2 right here. So let's fix that. 2 on both sides. Oxygen, since this 2 right here counts for everything after it, the lithium hydroxide, I have 2 oxygens here. On the product side, I have 1 oxygen here, and I have 1 oxygen right there. So now I have 2 oxygens on both sides, which is great. And then finally, hydrogen, same thing. This 2 counts for everything. So I have 2 hydrogens, and all my hydrogen is in the water, which has 2. So 1 and 1, everything is balanced out. Okay, this next one looks pretty complicated, but it's actually not that bad. We're in luck. The cyanide, that was, the cyanide stays together on both sides of the equation. Okay. And then the bromide, which is not in your polyatomic ion sheet, but that's okay because it's more than 1 atom. It's polyatomic ion. We can see that it stays together on both sides. Okay. So I can balance those as one thing. I can balance A, N, SN, and BrO3. You can even rename these as X and Y if you want to. That way, what's inside the polyatomic ion doesn't become confusing if you have, say, other things in there that also have oxygen. You don't want to count those while you're doing your balancing. You want to think of it as one thing. Okay, so GA, I have 1 right here. I have 1 right here. So that's good. Cyanide, I have 3 here. And on this side, I have 4. So what I need to do is think about at what point can 3 or 4 come to the lowest common denominator. If I put a 2 here, that's 8. 3 is never going to equal to 8. If I put a 3 here, then 3 times 4 is 12. So I can have 12 cyanides. And on this side, if I put a 4, 4 times 3 is also 12. So I can balance those at 12 apiece, and I'm happy. And again, this does throw off my original balance of, there we go. This throws off my original balance of the GA, but I am not going to worry about that for now. I'm just going to go ahead and press forward and finish my balancing and then go back and see if I need to do anything. Okay, let's take a look at SN. I've got 3 here because I put a 3 in front as a coefficient. I have 3 of these and I have 1 on this side. So I'm going to go ahead and put a 3 here, and that balances these. And then finally, my last polyatomic, BrO3, I have 3 on this side. And on this side, because that 4 is there, 3 times 4 is 12. And so just like on the other one, if I put a 4 here, 4 times 3 is also 12. So that balances those. Now let's go back real quick and take a look and see if this balanced itself out. And it did. I have 4 on this side, and I have 4 on this side. So that's good. Cyanide, 4 times 3 is 12. 3 times 4 is 12. Those also balance out. So we're in good shape. Okay. Here, nitrate, NO3, it stayed together on both sides. So I get to think of it as one thing. Let's take a look at calcium. 3. And then also my iron. Okay, so calcium right now I have just 1 on this side, and I have 1 on this side. Okay, so that's fine at 1. Nitrate here I have 2. So there's NO3. The 3 relates to the oxygen, but this 2 relates to whatever it's touching. And it's touching the parentheses, so it relates to everything in there. So I have 2 NO3s. Here I have 3 NO3s. Okay, so I'm going to do basically the same thing I did in the last one. If I put a 2 here, I can have 6, which is now an even number. And if I put a 3 here, I can also have 6. And I have 6 on both sides. And then my iron, I have 1 here. And on this side, I have 2. And this is a good, easy one to change. I can just put a 2 there. I have 2 on both sides. So since we made some changes, let's double check our calcium. Where's that at? There we go. Calcium, because I put a 3 here, I now have 3 of these. And so I can just put a 3 here. And now I have the same amount on both sides. And I have 3 and 3, 6 and 6. Iron is at 2 and 2. Okay. All right, I've got aluminum, I've got hydrogen, I've got chlorine. Nothing stayed together, so I'm going to break that up into aluminum, hydrogen, and chlorine. Aluminum, I've got 1 here, and I have 1 here, so that's fine. Hydrogen, I have 1 here, and I have 2 here. So let's go ahead and put a 2 here. And now I have 2 on both sides. Chlorine, where I had 1, I now have 2. But here I have 3. So let's go ahead and make this an even number so I can make that work. Let's put a 2 here. 3 times 2 is 6. And so now I'm going to have to go back and revise this and put a 6 here instead. So that brings my chlorines to 6 at a piece. So let's double check the aluminum. I've got 2 on this side now. So let's go ahead and change that to a 2. So 2 apiece. Hydrogen, I now have 6 hydrogens. So here I have only 2, but luckily that's an even number, so that's an easy fix. Let's put a 3 here. 3 times 2 is 6. I have 6 on both sides. And then double check our chlorines, make sure we didn't mess anything up here. 2 times 3 is 6. And here 6 applies to both the hydrogen and the chlorine. So I have 6 on both sides. And so this is balanced. Go ahead and clean this up. At 2623. This can't be reduced. So that is our numbers. If for some reason when you were doing the math, say you came up with 4, 12, 4, 6 or something like that, which is double of each number, make sure that if you can reduce them, that you do. But in this case, that's not an option. Okay, last one. We've got this polyatomic, C2O4, which stays together as C2O4. That's great. IO3, IO3. Everything stays together. So okay. All right. Got one here. I've got one here. So for now, that's good. I've got one here. And I also have one. So that's good for now. My potassium. Got one here and I have two here. We had to eventually have something to balance, didn't we? Let's put a 2 here. So that's good for now. Okay. And then here I have 2 on this side. And on this side, I had 1, but since I put that 2 there, I now have 2 on this side. So that's great. So that's balanced at 2. Let's double check our first one, or let's go back and just double check. So for the BA, we've got 1 and 1. C2O4, I've got 1 here and 1 here. Potassium, I've got 2 here and 2 there. And that gives me 2 of that polyatomic. And I already had 2 of that one. So everything's good to go. And those are my coefficients. 1, 1, 2, 1, and 1. Okay, now we're going to get a little bit more difficult. We're going to get into predicting. Okay, first thing I want to do is take a look at what it is I'm working with. So I've got zinc, Zn, and that has a set charge of +2. I have that on my in-class periodic table. Remember, we can do a +1, +2, +3, ±4, -3, -2, -1, and then 0 for here. We have several with variable charges. All of those. And then we do have some with fixed charges. And these are written on the table in the classroom. But you can remember these go down +3, +2, +1. And we do have others, but we'll take a look at that. Okay, and then lead 4. So lead is a variable charge, but we know what the charge is because it's lead 4. And then chloride, that's I, so that's going to form a Cl, and that's going to form a -1 charge. Okay. So first thing we want to do is see, is zinc strong enough to break the bond with lead? Well, let's take a look at our activity series. Okay. Let's find zinc. Here it is. And let's find lead. Here that is. So zinc is a higher on the activity series than lead is. So this reaction will occur. And what's going to happen is the positive must go with the negative because like charges repel. So zinc is going to bond to the chlorine. And since we're answering this in words, instead of doing that, what we're going to do is write zinc chloride And then the lead is going to be left all on this little lonesome. If it's a solid, the charge is not important. So plus lead. So let's take a look at this one. We got silver and sulfuric acid. And we haven't really gone over the naming conventions for acids, which is why we're putting the formula here for you. So this is going to break apart. You have your silver, and the silver has a set charge of +1. And let me show you real quick on our periodic table. So you have your aluminum, zinc, and silver. I'll just kind of follow a path going down. And then this one here, the CD also forms a +2. So those have known charges. You don't have to write a variable for it, but a little bit harder than just being able to tell by what column it's in. Okay, so silver forms a +1, and sulfuric acid is going to break apart into hydronium and sulfate, which is SO4 -2. So before we do anything, we want to look at our reactivity series and see if silver is strong enough to break up a compound with hydrogen. And here we go. And silver is not. Hydrogen is right here, and silver is below it, which means silver is not reactive enough. So for this one, my answer, I'm just going to put, oops, no reaction and move on. Okay, barium. So barium, I'm going to look at my periodic table. Okay. And barium is element number 56. And barium forms a +2. And then water, I like to write water as H/OH, hydrogen hydroxide. And that splits into hydronium and hydroxide. So once again, hydrogen, let's see if barium is reactive enough, and it's all the way up here. So definitely that reaction is going to happen. And so I've got hydrogen and hydroxide as options. Like charges repel each other. So this barium really only has one option, and that's to bond to the hydroxide. And barium is a +2. So I'm going to need 2 hydroxides. So if I was writing this as a formula, I would write it like this. And then what's left is your hydrogen. That's all by itself. And the hydrogen is diatomic. So I would write it like that. But the question asks for it in words. So that's actually a little bit easier. Barium hydroxide plus oxygen. Okay. Tin and hydrochloric acid. So tin is SN. And tin is a variable charge. It can form a, I believe it's a 3 or a 4. Let's double check. Okay. So tin and lead both have variable charges. Okay. And they can form, a +3 or a +4. So in this case, since the question doesn't specify one, we're just going to go ahead and pick one. Why not? So let's do +3. Okay. Hydrochloric acid, this is going to break up into hydrogen and chlorine. And once it has a charge, it's now chloride. Okay. And I'm going to look at my reactivity chart. I'm not going to pull it this time. I'm just going to take a quick look at it, make sure I'm right. And tin is above hydrogen. It's about 2 steps above it. So this will work. So SN +3 and Cl, I'm going to need 3 Cls. If I was writing this as a formula, I would write it like that. But since I'm not, I'm going to put it in words, and I use a +3. So that makes this 10-3. 10-3. And it is bonding to chlorine. So chloride, ide, plus hydrogen. Whoops. Which, if I were to write that, I would remember that's a diatomic. So that would be H2. Okay, gallium bromide plus fluorine. Okay, so in this case, I've got gallium, which is, let's find that one here. And the actual number for it. Sometimes you got to do a little hunting. Okay, gallium, element number 31, that forms a +3. And then bromide, which is Br, which forms a -1. And in this case, we're doing fluorine. So fluorine, or whoops. Okay, and there actually is a reactivity chart for nonmetals, but since it's not part of our um, forms, we're just going to go ahead and assume that the reaction will take place. So if fluorine breaks apart this compound, which one can it go with? Well, like charges repel, so it's going to have to be the gallium. Positive comes first. Okay. And then the bromine is going to end up on its own. Okay. And one thing to pay attention to is bromine, Br, is one of our diatomics. We have those. Plus, of course, hydrogen, which always loves to be the exception. So if I was writing that as a formula, I'd be sure to put Br2. But this is gallium with fluorine. So gallium fluoride plus bromine. So it's no longer connected. So it goes from ide back to its original spelling, which is bromine, Bromine. That's it for those. Let's take a look here. Predicted products in words, the following double replacement reactions. Now, double replacement, we don't have to worry about reactivity series anymore, so that's nice. Let's take a look what's there. Sodium hydroxide and nitric acid. So in this case, the hydrogen is going to split off, and we're going to be left with nitrate, NO3. Okay. And so they're just going to swap partners like dance partners here. So Na plus is going to go with the nitrate there. Okay. And that's going to be a 1-to-1 ratio. And so that's going to be sodium nitrate. Okay. And then what's left is we have our H plus hydrogen and our OH minus. So that would go together H/OH, which is my favorite way to write water. So sodium nitrate plus water is going to be our answer. Okay, let's clean that up a little bit. Okay, silver acetate. So Ag is silver, that forms a +1. And then we're going to look on our periodic table because it's acetate, there's no ide there. So that's CHO232. And then you're going to look at the charge for that. It's going to be negative charge. And then 10-4, SN +4. And then nitride, IDE. So that's just nitrogen, which forms a -3. Okay. So if I was putting these together as formula units, I would pay very close attention, make sure I do my swap drop. So I put my silver with my nitrogen, and then I would put my tin with my acetate and make sure that I put it together correctly. But in words, I can just say silver nitride plus tin for, very important, otherwise you won't know how to put it together, acetate. Okay, and there's our answer. Okay, lead 2 iodide. So lead 2 Pb with a +2 charge. That's what the 2 means. Iodide, that's just iodine, and that forms a -1 charge. Strontium, which is Sr, forms a +2. Carbonate, okay, remember that's an 8. So I want to look at my periodic table and make sure, or I'm sorry, look at my list of polyatomic ions and see what carbonate is. And carbonate is CO3 with a -2 charge. So I'm going to put my positive with my negative. Okay, and so that's going to be lead 2 carbonate plus iodine and strontium. So iodine, I'm sorry, whoops, oops. Thought that sounded weird. So strontium, positive always comes first. Strontium iodide. Okay. And so at this point, you should be able to go pretty quick. So zinc, Zn, we talked about that earlier. Zinc has a set charge, it's +2. Oxide, so it's oxygen with a -3. Cobalt, which has a variable charge. In this case, it's 3. All right, because you have your 3 here. And nitrite, ITE. So just look at my periodic table, -3. Okay, so I'm going to put my zinc, which is my positive. We're just going to swap partners. So zinc is going to leave the oxygen and bond to the nitrogen. And so that's going to be zinc nitrite. Plus cobalt 3. And that's going to bond to oxygen. So cobalt 3 oxide. So just as a review, let's take a look and see how that would go together. So you have zinc with a positive, you have your nitrogen, N-3. Do my cross drop, it's going to be Zn3N, and then cobalt 3, CO +3. Oxide is a -3, so those can cancel each other out and just be like that. But that's not what the question was asking, just kind of doing a quick review. Calcium hydroxide. Calcium forms a +2. Hydroxide is OH-. Phosphoric acid. So this is going to break up into hydronium with its H+, and phosphide, O4 -3. That's phosphate. You'll see that on your polyatomic ion sheet. So if we swap ionic partners, calcium comes first. Calcium phosphate. So in this case, I had to know PO4 was phosphate. If you're not sure, make sure that you, when you see a polyatomic ion, which PO4 is obviously poly, has more than one atom in it, make sure that you look up the name of those. So calcium phosphate plus hydrogen and hydroxide, as we saw before, is HOH, or water. Okay. Hydrochloric acid, H plus, Cl minus, aluminum forms a +3, hydroxide is OH. So let's go ahead and, in this case, usually you put water at the end, but it doesn't really matter. It's still the two compounds are going to form. But let's just go ahead and put aluminum and chlorine together. So aluminum plus water. Our aluminum, our positive, is going to bond to the negative, and we're left with water. All right, almost done. Let's take a look at a couple of combustion reactions. And for this, you might want to write this on a separate piece of paper, but let's go ahead and look at what the products, and this is in your notes. But I have carbon, I have hydrogen, I have nitrogen, I have sulfur as being my possible reactants. And each one of those is going to tell you what is going to be in your products. If there's a carbon, which there is right here, then it's always going to form CO2 in a combustion reaction. Combustion meaning that it's reacting with O2, which is true for all of these. And if there's hydrogen, which in case there is, it's going to form water, which you can write as H2O, or you can write as my favorite, HOH. In this case, it really doesn't matter because you're not breaking it back apart. Whatever you're more comfortable with. Okay. So, and then it asks us to balance the reaction. So let's do that. I've got CHO. I don't have anything that stayed together. So I have 2 carbons on this side, and I have 1 carbon, all my carbons in the CO2. So I have 1 carbon here and 2 on the other side. So let's fix that and put a 2 there. Now I have 2 on both sides, which is great. Hydrogen. I have 6 hydrogens right here because of that 6. And I have 2 here. So I need to turn that into 6. So 2, 4, 6. Let's put a 3 in there. So now I have 6 and 6. And now oxygen. And this is where mistakes are easy to do. First off, there's 2 and 2. So 2 times 2 is 4. So I have 4 oxygens in my CO2. But let's not forget, I've also got 3 oxygens in the water. So plus 3 equals 7. So altogether, I have 7 oxygens. Now I need to get 7 oxygens on this side, but I can only do them in multiples of 2. So what I'm going to do is go ahead and, if I could do 3.5, that would work, but I can't. That's just not legal. So I'm going to go ahead and double everything, and I'm going to do 7. So I have 14. And then once you do that, you double everything else. So this 2 becomes a 4. This 3 becomes a 6. Let's go ahead and clean things up a little bit. Okay. And then the unspoken 1 here becomes a 2. Okay, so 2, 7, 4, 6. I'm not done yet. Let's just clean it up so it looks a little better. Okay. 2, 7, 4, 6. Okay. So that gives me 14 oxygens on both sides. And let's double check the hydrogen, make sure everything's stayed balanced, or the carbons, right? Carbon, now I have 4 because I have 2 times 2. So I have 4 carbons on this side. And here I have 4 carbons because that counts for both. So I have 4 carbons, good to go. Hydrogen, 6 times 2 is 12. So I have the 6 here, 2 here, 6 times 2, 12. And hydrogen here, I have 6 hydrogens times 2. So there's 12. And then finally the oxygen, we just balanced at 14. So we're good to go. So that means my coefficients are 2, 7, 4, and 6. So there's 2 ways of doing that. You can either do the 3.5 like I did and double everything, or just think, what is your lowest common denominator? I find that to be the easiest way, but either way, it works out mathematically. Okay. C2H5N plus O2. So we already saw before, if there's carbon, which there is, I'm going to have CO2. And I've got my hydrogen here, so I'm going to have water. And then I have my nitrogen. Nitrogen's just going to be nitrogen. But very important to remember, that is one of the diatomics, so it has to be N2. It won't balance if you don't do that. All right, so let's take a look here. I'm just going to balance them as C, H, N, and then, whoops. So used to putting 2 there that I did it. Okay, so carbon, I've got 2 on this side, and I have just the 1 here. So I'm going to go ahead and fix that. I'm going to put that 2 here. I got 2 on both sides. Hydrogen, I've got 5 right here. And here I have 2. So I need to find the lowest common denominator. And 5 and 2, the smallest number they can both divide into is 10. So I'm going to go for 10 hydrogens on this side, and 5 times 2 is 10 hydrogens on that side. Now, notice that changes my carbon, but I'm not going to worry about that. I'm going to go all the way through and balance everything and then see what falls into place and what doesn't. So I'm just going to move forward after I balance the hydrogen. I'm going to take a look at my nitrogen. Nitrogen, because I put this 2 here, I now have 2 nitrogens on this side, and N2, I have 2 nitrogens, so my nitrogens are fine. So let's take a look at my oxygens. Oxygen, I have 2 times 2, so I have 4 in the CO2 and 5 in the water. So altogether I have 9. Now this is 2, so again, I can't make that into an odd number. I can't make it 9. So 9, it would be 4.5, which I'm not allowed to do. So what I'm going to do is just go ahead and double everything to make that work. So I can turn that into a 9, I'll turn that into a 4, 4, 10, and 2. If I do that, oops, everything's going to work out. So now in my carbons, I have 4 times 2, so I have 8 carbons on this side. Carbons here, I'm sorry, times 2 is 8. Oh, no, I actually do need to go back and fix that. So I have 8 carbons. Now in doubling everything, I did fix the oxygens, but the carbons still need a little bit of work. Okay, so I need 8 carbons, so I'm going to further change that. Actually, let's leave it there. Okay, and I'm going to make this an 8. So now I have 8 carbons on both sides. Hydrogen, 5 times 4 is 20. So I have 20. And over here, 10 times 2 is also 20. So I have 20 hydrogens. Nitrogen, I've got 4 on this side. And since I added that 2, I also have 4 on both sides. And then my oxygen, let's double check that because I did make a change here. I've got 10 in the water and and the 16 times 2 is 16, so 26. Okay, and that's oxygen 2. So I'm actually going to have to go ahead and add a little more to my oxygen, but this time it's an even number, so it's a lot easier. So 13. So as you can see, sometimes you have to go back and forth. It can get a little complicated. Maybe there was an easier way to do it, but at the end of the day, this did work out. We have 4, 13, 8, 10, and 2. So this is about as complicated as they can get. Okay, H2S and O2. Let's go ahead and clean this up a little bit. So I know if I have sulfur, this is the last of the 4. So sulfur is going to form so 2, and hydrogen will continue to form water. Okay. All right, let's see. HSO hydrogen. I have 2 here and 2 here, so that's good. For now, they're good. Sulfur, I have 1 here and I have 1 here, so that's great. Oxygen, I have 2 plus 1 in the water, so altogether I have 3. So I'm going to do my same trick. 1.5 doesn't work, but I can double that to 3 and then change everything else from 1 to 2. And there we go. 2, 3, 3, 2. So that one's a lot quicker and easier. Let's go ahead and double check. Hydrogen, 2 times 2 is 4. On this side, it's all in the water. I have 4 there. Sulfur, I have 2 because I added that 2. Now I have 2 sulfurs in the SO2, and the oxygen we just balanced at 6 apiece. And HCN plus O2. So we already know hydrogen is going to form H2O. We know carbon is going to form CO2. And we know nitrogen is going to form N2. So let's take a look at what we got here. H, C, N, and O. All right, so right now for hydrogen, we have 1 on this side and we have 2 on the other side because of that 2. So let's fix that, put a 2 there. Now we have 2 on each side, so we're good to go on the hydrogen. Carbon. Carbon, because I put that 2 there, now I have 2. And in the CO2, I only have 1 right now. So let's go ahead and put a 2 there. And now I have 2 carbons on each side, so that's good. Nitrogen. Again, I put that 2 there, so I have 2. And here and 2, I have 2 nitrogens. So nitrogen are balanced. And then let's take a look at the oxygen. Here I have 2 times 2. So I have 4 oxygens in my CO2. But let's not forget the water. I have 1 there. So I actually have 5 oxygens. Okay. And so I want to balance those out a little bit. Now I can't do 5 in multiples of 2. If I were, then that would be what, 2.5. But I'm not allowed to do that, but I can double everything. So 5 for water goes from 1 to 2. Your CO2, let's clean this up a little bit. Your CO2 is going to go from 2 to 4, and your N2 will go from 1 to 2. So let's double check that, see how that worked out for us. Hydrogen, we have 4 now because we doubled it. 4 hydrogens, and 2 times 2 is 4, so 4 hydrogens on both sides. Carbon, we have 4 carbons, And on this side, all of our carbon is in the CO2. Hey, arrowhead's already there. So 4 carbons. Nitrogen, we have 4 nitrogens. And 2 times 2 is 4, so 4 nitrogens on both sides. And then our oxygen, 4 times 2 is 8. So we have 8 there. And then in our water, we have another 2, so 10. And 5 times 2 is 10. So we have 10 waters on, or I keep saying water, oxygen, 10 oxygens on both sides. And so we're good to go. So our balanced equation is 4, 5, 2, 4, and 2. Last one. All right, so we know hydrogen is going to make water. We know nitrogen is going to make nitrogen gas, or N2. And then the sulfur is going to form SO2. NHSO. Nitrogen, I've got 1 on this side and 2 here. So let's go ahead and make that a 2. We have 2 on each side. Hydrogen, all of them in the water. So I have 2 on this side. And since I put that 2 there, I have 2 on both sides. So great. Sulfur, I've got 2 here and only 1 here. So let's put a 2 there. 2 on each sides. And then let's count out our oxygens. Okay. I've got 1 here in the water, and 2 times 2 is 4. So I have 4 plus 1. So I have 5 oxygens. And I can't really turn a 2 into a 5, right? But I could do, if I was allowed to, I could do 2.5, but that's not really a thing. But I can double everything. So 5, 4, the 1 becomes a 2, 1 becomes a 2, 2 becomes a 4. And let's take a quick look, make sure everything's right. So let's clean this up a little bit. Oops. Okay. So I've got 4 hydrogens. And on this side, 2 times 2 is 4. So I've got 4 hydrogens. Oh, I skipped ahead to hydrogen, but oh well. 4. For my nitrogen, I've got 4 here. And 2 times 2 is 4, so 4 on both sides. And for my sulfur, I've got 4. And here I have 4. So we're good. And for my oxygens, I've got 5 times 2 is 10. And I've got, on this side, I've got 2 right there. And so need another 8. And 4 times 2 is 8. And so that's 10 on both sides. 10 and 10. And there we go. Our balanced equation is 4, 5, 2, 2, and 4. Okay, so hopefully you got something out of this. Hopefully it was helpful for you. We are going to go through this in class as well. If you can think of any questions, please write those down and we will work together to solve them. So that is